Our next speaker is Pierre Le Doussal, who will speak about the paradoxical title of trapping fermions but leaving Gaussian free.
Thank you. So I will discuss some aspects of counting statistics of fermions in a potential, in an external potential. So I will describe the results of this, some of the results in these three papers, three recent papers. The second paper here was done in collaboration with Jan Fyodorov, and was also borrowing heavily from previous work with Fyodorov and Shanyu Kao. The first and last paper were made in collaboration with Satya Majumdar and Gregory Scher, and with Naftali Smith, who was postdoc at École Normale, and he's now in Ben Gurion University. So I will, yeah, just before. So the subject of counting statistics of fermion is not really a new subject, of course. There are many papers, and I will not have time to do any review of it. So I apologize in advance for reference that I missed, but I'm pretty sure you can find them in these papers where we try to be more exhaustive. So I will focus on things which I believe are new, I hope. So I will start with non-interacting fermions in one dimension and consider arbitrary potential, but confining, so that the density of the Fermi gas has a bulk region and then an edge region beyond which it vanishes. And I will study the quantum fluctuation of the number of fermions in a given interval. I will study, for instance, the variance of this number, which will have various regimes. And it will be based on a semi-classical calculation, very simple, which I will show, which leads to a connection with the Gaussian free field. And so for some very special potentials, such as the harmonic oscillator, for instance, there are connections to random matrix theory. I mean, the position of the fermions can be seen as eigenvalues of random matrix. And in that case, there are no, for instance, for the harmonic oscillator, it's a GUE ensemble. So it has beta equal 2, and there are no interaction in that case between the fermions. So in that context, this connection with Gaussian free field was well known for some time, but we have kind of generalized it to arbitrary potential V of x. And I must emphasize this actually is a Schrodinger, the potential Schrodinger equation. It's not the potential of the matrix model. Huh? So it's a different object. So one of the applications will be to obtain this variance in any dimension for central potential. The second topic will be slightly different. I will now look at the number of fermions in an interval, but as a function of the edge of the interval. So it will define some height field, counting height field. And I will focus first on a unitary ensemble, C beta E, for arbitrary beta. And this field actually has property of being a log correlated field, which is the question we're going to ask is about the statistics of the maximum of this field. So the maximum deviation from the average number of fermions. And this type of question in log correlated field have been quite popular in the last 10 years. And they're related to maxima of fractional Brownian motion with Hurst index 0. And the tool to address this question is to use statistical mechanics and freezing transition. There is a twist in the present problem because we are going to see the fact that you have fermions will be important and will give some variation with respect to some other models. And when we will solve this problem, we will express moments of the partition sums. And in fact, they are related to full counting statistics of interacting fermions. So this will allow me to jump now to interacting fermions in one dimension and obtain full counting statistics for some, which means higher cumulants of this number of fermions in an interval for a certain number of models. And then at the end, I will go back to non-interacting fermions and discuss entanglement entropy. Okay, so let's start with the counting statistics for non-interacting fermions. So first of all, why is there a recent interest in non-interacting fermions? After all, it looks like a trivial problem, but it's not quite, because if you put them in a trap with some potential, then the Fermi gas has an edge, and at the density, at the edge, the density vanishes, so there are strong fluctuations, and the standard approach fail. So one has to develop other methods, and we have been working a lot on the correlation at the edges, and there's also a lot of work on inhomogeneous bosonization by Dubai and collaborators. So there are some fundamental theoretical questions for this problem, and there are also relation to random matrix theory, and as we have heard in a previous talk, to KPZ equation. And the second motivation is that it can be observed in principle in the cold atom experiments, provided you can motivate them to do it, which we have not yet succeeded completely, but I think they are more interested in solving high TC superconductivity. But one day maybe they will do this experiment. It's certainly not a technical problem. They can do it. They can have harmonic traps, arbitrary shaped traps. They can reach non-interacting limit. For fermions, they can reach very low temperature, and they can image a position of fermions in 2D or 1D. For instance, with this fermionic quantum gas microscope, which has been around still 2015, they can count how many fermions there is in each of these small box, and count how many fermions you have in a domain and measure the quantum fluctuations. Okay, so let me just remind some very simple things about fermions in ground state of fermions in a harmonic trap, just to start. So you have the single particle energy levels of this Hamiltonian harmonic oscillator, which are labeled by K. And the n particle fermion wave function is defined as a Slater for the ground state, is defined as Slater determinant, where you feel which involves the n lowest levels, wave functions in terms of Hermite polynomials. And now the connection to the GUE in that case is the following. I mean, you can rewrite this wave function, this Slater determinant. You can, with Hermite polynomials, you can massage it into actually a van der Monde determinant. And so then the probability distribution, the quantum probability distribution of the fermions in this harmonic well has this form, and this form, of course, is the same form as the form for the eigenvalue of a GUE random matrix, so beta equal 2, so that the position of the joint distribution of the fermion position up to a scale, up to a rescaling are exactly is the same as the position of the eigenvalues. Okay, so this has generated some work where we're just able to translate known result from random matrix theory to fermions. Now this extends to other potential. For instance, the Laguerre unitary ensemble corresponds to this x squared plus 1 over x squared potential for positive x. The Jacobi unitary ensemble corresponds to a fermion in a box with some inverse sign potential, and so on. So let me describe now the correlation of fermion in a general potential. So again, we have this Slater determinant in the ground state, and the psi k of x here are the eigenfunction of this Hamiltonian, single particle eigenfunction of this single particle Hamiltonian. Now, the square of the quantum probability is the square of the wave function. So you can, since the product of determinant is determinant of product, you can rewrite it as a determinant of a kernel, this object, which is constructed from the n lowest level of the Hamiltonian. And I will use indifferently either notation kn or k mu. So you can either fix the number of fermions, or you can fix the Fermi energy, meaning that all the levels below this energy are occupied. At 0 temperature, there's no difference, the same thing. So how do you obtain correlation? Well, all the endpoint correlation function, which are defined like this by integrating the position of all the fermions except small n of them, well, they can all be written as determinant of this kernel. So if you know the kernel, you know all the endpoint correlation function. And in particular, the density is just a diagonal part of the kernel. Okay, so let's go to counting statistics now. And first thing, simple thing is the mean number of fermions in some interval, in some domain. And of course, it's equal to the integral of the density in this domain. And I'm going to be interested in the limit where the number of fermions is large in some given potential, or the Fermi equivalently, the Fermi energy is large. So in that limit, you are looking at high energy levels, and you can apply semi-classics or this local density approximation, which is telling you that in the bulk, which is a region where the potential is smaller than the Fermi energy, the density is given by this formula, where kf of x is a local Fermi momentum. And this LDA density vanishes at and beyond the edges, which are given by this expression. And of course, there is some non-trivial way in which it vanishes with some fluctuation, but I'm not going to talk too much about that in this talk. I will focus more on the bulk. The relation between the number of fermions and the chemical, the Fermi energy mu is just simply this normalization condition. And of course, for the harmonic oscillator, which is the same thing as the GUE, if I look at the density divided by n, so normalized density to 1, then it goes, in a larger limit, it goes to the semicircle with these edges. Okay, so now let's go to the variance. So how do I calculate the variance? Well, there's this formula for the variance in terms of the square of the kernel. Now, of course, the variance of the number of fermions has something to do with the 2-point correlation of the density. And since it's a determinantal point process, as I mentioned here, this 2-point correlation is given by the square of determinant and 2-by-2 determinant. So it has to involve the square of the determinant, the square of the kernel, sorry. And this has a different, okay, and you have to subtract some parts. So that's why the x here has to belong to the domain and y to the complementary of the domain. So this is a general formula valid for any determinantal point process. And so there are, depending if you choose your domain to be microscopic scale or macroscopic scale, so small scale or large scale, as compared to the, so small scale mean of the same scale as interparticle distance. So on this microscopic scale, the kernel has a universal limit, which is the so-called sign kernel, which I'll show later. And from this sign kernel, if you calculate this variance, you find the result of Dyson and Meta for the GUE, for instance. So for the harmonic oscillator, you would find this formula when you are in a microscopic regime, but this separation here is still number over the 1, but large. And this is the Dyson Meta constant. So there's a log n part, and then there is a constant part plus something which decays to 0 at large n. And the question will be, in this talk, will be to obtain formula also in the macroscopic, at macroscopic scales, meaning in the same order as the support of the measure, support of the density. So for this, we're going to introduce the height field, which is a number of fermions which are on the left of a given point x. And interested to calculate the covariance of this height field. So there is actually an exact relation for this non-interacting case, which relates the square of the kernel to the height field. And once you know the covariance, I mean this covariance field, you can calculate, I mean, you obtain immediately the variance of the number of fermions in any interval or any collection of intervals just by this type of combinations. So our objective will be to calculate this covariance field and on a macroscopic scale. And okay, so as I said, we're going to look at a large number of fermions, so we can look at states which are at high energy in this trap. And so we can approximate them. So it's reasonable to approximate them by their semi-classical WKB form. And then with this form, we want to calculate the kernel. Okay, so in this, this CK is just some normalization constant. This is just the energy of the level. This is a wave eigenfunction. And this phase here is the WKB phase, which is given by this formula. And X minus here is the one of the endpoint of the density, so one of the edge. And I'm going to look at the case where there are two edges. So a single support, Now this WKB phase actually is of the order of n. I mean, so it's oscillating very fast and it's large. So what we're going to do is we're going to relabel our states and from the Fermi energy. So we're going to, so this kernel here, the states are filled up to nth level, the Fermi energy. And we're going to look at the highest energy states and use this relabeling. So we write the kernel like this. And we're going to see that the sum over M here somehow is convergence. So in some sense, the high energy states are the ones which are going to dominate. So if you do that, well, you can write this WKB phase at level n, capital N. It has this form with a Fermi wave vector here. And we're going to do two turning point case. And so what are we going to do? We're going to expand this WKB phase around the Fermi level. So we're going to write this Fermi WKB phase for n minus m as phi n plus expansion. So this term will be of order n, capital N, and this term will be of order 1. And this derivative of phi n with respect to n, so phi n is this, mu is a function of n. So I can take derivative with respect to capital N here, and I can write it like this, derivative with respect to mu, and then dn d mu. D phi n d mu is given by this integral, because you see that what you need to do is to take the derivative of this phase with respect to mu, and you can use this relation here, which is obvious from the definition. So you end up with this expression, and then the denominator actually is equal to this, because total number of fermions is actually related to this integral from x minus to x plus, which are the two edges of the support. So at the end of the day, you see that this WKB phase is phi capital N of x plus something of order 1, which involves this field theta x. So this field is very important. It's will appear everywhere after that. So this is a definition of this field. So for any potential v of x, I can define this field theta of x, and it goes from 0 to pi when you go from one edge to the other edge of the support of the density. Okay, and there is this identity here which follows from the definition. Okay, so now we're going to want to, so we have this expansion of this phase, and we want to put it into the wave function and write the kernel. So if you do that, what will vary quickly are these signs. So these are fast variation. But the prefactor in this WKB here vary very slowly with k. So you can just approximate them by their value at the Fermi level. So you end up with this formula. And in this formula, what is nice is that you actually, it's a geometric series on M here, and you can perform this, this summation, and you get this expression. Okay, so this expression is the sum of two sine functions, which oscillate again very fast. So if you actually numerically calculate this kernel, you see that there are very fast oscillations. So this part here, so this is a point, the point reference point is here. So there is a, here it will be a sine kernel, and then it's decaying and oscillating very fast. But you see that there is an envelope here, and the envelope is not trivial. So the kernel has a very fast oscillation, but there is an envelope. And to get this envelope, what you want to do is to take the square of the kernel. That's what we want to do because we want to calculate the variance of the number of fermions. And if you compute the square of the kernel, you're going to square this expression. So the sum of the square oscillate very fast, so you can replace them by 1/2. But then there is a cross term which is just oscillating extremely fast and replaced by 0. So at the end of the day, so what you can do is a local averaging of the square of the kernel to obtain this envelope. And in any case, we need to do this local averaging because we want to calculate the variance of the number of fermions. And the nice thing is that it can be expressed as a total derivative with respect to this function theta x that I introduced. And as a result, it's possible to solve this equation on these macroscopic scales in a bulk. So x minus y are much larger than the distance between the particles. And then you obtain the covariance in this form. And the only thing we have assumed is macroscopic distance between x and y, and kf of x slowly varying at the microscopic scale. So this is valid in the bulk, and it gives you the covariance for arbitrary potential. Okay, and in fact, you can, if you go back to the definition of theta x and you plug in the harmonic oscillator, you find some function theta x, and at the end of the day, from this formula, you find the envelope, which is has this form. And this form actually was, in the case of the random matrix, so for very special potential, a quadratic potential, was obtained a long time ago by Brezin and Z and other people. In fact, when we started this calculation, we didn't know about these papers, but okay. So we have this form now for arbitrary potential. Just to show you that the same method allows to recover the sine kernel. Suppose now that we want, in the previous derivation, we are taking now the points close to each other, x and y. In that case, there's one of the sine which varies now slowly. And you can do just a simple derivative expansion on top and bottom, and you get everything cancels out, and you get the sine kernel. Okay, so we have studied small and large scale and found that there's nothing in between, actually. Okay, so now let me summarize. So we have introduced a height field for fermion, for the fermions in arbitrary potential, and we have this result for the covariance of this height field, where theta of x is this function. Okay, so now this is related to Gaussian free field in a relatively straightforward way. So Gaussian free field, two-dimensional Gaussian free field is I will not get into all the possible definitions, but it just sees as a Gaussian process on a two-dimensional domain with a covariance kernel, which is a green function of the Laplacian. And here the domain, to recover this formula, the domain has to be chosen to be the upper half plane with Dirichlet boundary condition on a real axis. And then you see that this function is just the same as a correlator of the Gaussian free field if I make this correspondence here. So what does it mean? It means that if I want to have the covariance of the height field at different points along my original problem, where the support of the density is between these 2 points, then I can look at the two-dimensional Gaussian free field inside the upper half plane with Dirichlet boundary condition, and look at under this mapping, I can read off from this formula the correlation. Okay, so there's a map from the interval to the unit circle in a complex upper half plane, and the fact that it's Dirichlet boundary condition, I think, is related to the fact that the total number of fermions inside the support is fixed in a ground state. Okay, so this is just our production in the case of the harmonic oscillator, where the map is just this one. And then it turns out that for the harmonic oscillator, this is actually a very well-known result. And it goes, this is a very nice slide from one of Alexei Borodin's talk. And since the work of Borodin-Ferrari and Borodin and Guyonnet, it is known indeed that if you look at, for instance, very large or infinite GUE matrix, and you look at the corners, the corner matrices, truncated matrices here, look at their spectra, so they form this pattern. And so this would be a GUE1, this would be GUE2, GUE3, GUE, and so on. So each line here is a GUE-n, and you can define a height field in a similar way we did. So each line will be like what we are studying, the fermions, if you want, on this on each line. 1 fermion, 2 fermions, 3 fermions, and so on. You can define a height field in 2 dimensions. And you can look at the large scale limit of this. And if you do that, you find that it was proved by these authors that the covariance, I mean, the height field actually goes upon proper scaling to the Gaussian free field with this map, with this correspondence. So this map is exactly the same as this map, actually. So it maps a line here, a horizontal line, which is GUE eigenvalues, to a circle. Okay, so this answers the question of what is the direction transverse here. I mean, you have after all you have a Gaussian free field, so x is original coordinate of your fermions, but now there is an additional direction, and somehow this additional direction is in this model is interpreted in a simple way. It's just corner matrices. So we don't have an interpretation in terms of fermions of these other rows. I mean, real life fermions, I mean, that you can study in experiments, for instance. But if somebody finds one, it would be very nice. Okay, so this line, this axis is like the number of fermions, if you want, in this this model. Okay, now there are also connections to the work of Dubai and collaborators on inhomogeneous bosonization, which probably was mentioned before in this conference, but I won't get into it. But they have also a function which essentially has the same property as our theta of x, but the way they derive things is somewhat different. So, okay, so now let me, since we have the covariance, we can calculate a covariance function. We can calculate the variance of the number of fermions in some intervals. But you see from this formula that we are not finished, because we have computed, even if this interval has a macroscopic size, is a large interval, we need still the height fluctuation at the diagonal part of the height fluctuation. So we need the expression of this for A minus B microscopic. So to do that, we go back to this equation, which is exact, and insert the sine kernel on the left. And we can solve that. We can solve this in a whole microscopic regime. So it has this form so that it matches what we have in a macroscopic in a large scale. And it remains, so the only thing we have to do is to solve this differential equation with this some boundary condition. And this last boundary condition comes from this delta function here. Okay, so you can do that and you get this function. And from this function actually contains this Dyson meta constant, its value at 0. And you can indeed calculate the variance for a microscopic interval, and you recover the Dyson meta formula. And more because you have a full scaling function. And then you can plug this into the formula for the variance of a macroscopic interval. And these are the main result of our first paper, which is a general formula for this variance. And it contains a leading order term, which is like log n. So this kf here is like is large. It's proportional to n if you want. So this is like log n number of fermions plus a finite part, which itself depends on the potential, precise detail of the potential, and which you can calculate exactly like this. Okay, so we have made some checks, and I'm not going to get too much into it, numerical checks. But most interesting thing was this application to higher dimension. And until what time is this? What is the final time? More than 10 minutes. Okay. Okay, so this is going to go very fast from now on. So you can look at the number of fermions in a sphere in d dimension now. And the reason why you can do something is that the angular modes fluctuate independently. So you can show that the variance, or even any cumulant of the number of fermions in this sphere is given by sum over a collection of one-dimensional problem in each angular sector. And since we know how to solve this problem now, to compute variance for this, we can compute variance in d dimension. So let me go very fast. We have variance for free fermions. So this most simple case. So this leading term was known before, but this constant was not known. So we have this constant. And we have for free fermion, in fact, we have the full exact result. And now more interesting for the harmonic oscillator, for instance, we have to solve these one-dimensional problems now become this r square plus 1 over r square potential, which are related to the Laguerre-Wishart ensemble. And by performing this summation, one obtains this type of results. So the variance of the number of fermions is now mu to the power d minus 1. Mu is large, it's a Fermi energy times log mu, times the prefactor, which depends on the ratio of r to the edge, to the size of the Fermi gas, plus some non-trivial function, which is this subleading term. And we have checked all of this numerically, and it works very nicely. Okay, so now let me come to another topic, which is extrema of counting staircase. So it's again the height function, but now I'm going to look at the circular geometry. So it will be eigenvalues on unit circle for the unitary beta ensemble. So the distribution of probability of this eigenvalue is known. It has this form, and the construction of this ensemble goes to these papers for beta different from 2. And this is equivalent to a problem of fermions now with in the Sutherland model of fermions. So it has now for beta different from 2, it is actually interacting. And for beta equal 2, it's just free fermion on the circle. So we're going to look at this staircase, meaning the function, the number of eigenvalue inside some interval as a function of the endpoint. So it's a staircase like this, which jump by units. And we're going to subtract the average. So we're going to have a field like this. And in a large n limit, large matrix size limit, it is actually a log correlated field. And we are going to ask a question of statistics of the maximum. Okay, so it was indeed shown in these papers for beta equal 2 and for general beta that this counting field using the characteristic polynomial actually has the statistics if you take x1 different from x2 and the joint probability at different points and n going to infinity for fixed x1 and x2. It has the form of a logarithmically correlated field. And this would mean that this would be a macroscopic regime because x1 and x2 are not scaled like x1 minus x2 is not scaled like 1 over n, but like 1. So at scales which are macroscopic, which means of the order of the size of the circle, then you have this logarithmically correlated field, which one can see as a fractional Brownian motion which has the spinning condition. And we're going to look at the maximum value of this field on some interval. And the only case we can really solve is the case where the interval is a full circle, which corresponds to a fractional Brownian motion bridge, or the case where the interval is relatively small, but still bigger than 1/n, which is fractional Brownian motion on an interval. Okay, so let me go relatively fast on this. I will introduce partition sum, which will depend on the an inverse temperature, which I call small b, because the letter beta is already taken by the Dyson index. Okay, so b is inverse temperature. And it's easy to see that when b goes to infinity, this is dominated by the maximum. So the maximum value of the field is given by the infinite b limit. So zero temperature limit, if you want. So we can calculate the moments of this partition sum. And the moments of this partition sum, for this we can, we're going to end up with this, so n replica, we're going to end up with average of these types over the C beta E ensemble. And this product here is for the eigenvalue of the C beta E ensemble. And average of this type are, of course, well known for beta equal 2. They are given by Toplitz's determinant. And this is called a symbol. When the symbol is smooth, then there is this Fego theorem. But for singular symbol, which is the case here, we have jumps, since they are characteristic functions. There is a Fisher-Hartwig method, and which was proved here. And what we're going to do is we are going to use a beautiful conjecture of Forrester and Frankel, which extended this Fisher-Hartwig result to any rational beta. So what does this conjecture will give us? Well, it will, for any rational beta, it will give us a formula for this, okay, it will give us this formula for this expectation of this product. So first of all, I can write this formula for n equal 1, just one replica. And applying their formula, one actually gets this. So the dependence in B here is telling you that there are some factors here which are just coming from a Gaussian fluctuation of this delta n, which are this B square factor. So this is what we had before. I mean, the variance. This is coming from the macroscopic fluctuation. But this factor here are actually coming from the small scale fluctuation, microscopic fluctuation, and they have this complicated form here for arbitrary beta. So this is really coming from their conjecture upon some translation. And so this will give you actually, for one replica, will give you the full counting statistics for the number of fermions in an interval in Sutherland model. For okay, so it was known. There are these two cases which were already known. One was by Jean-Marie here, and now this formula is a bit strange because there's a, if it's not obvious from this, immediately obvious that it's actually going to be continuous function of beta, but we have actually studied this formula in detail and found that it's perfectly continuous, and we found some simpler way to write it for any real beta, which is quite useful. And now if you look at any number of replica, you get this type of formula. So in addition to this Forrester-Frankel terms, there is also Coulomb gas integrals, which come from, again, from the large scale fluctuations. How much time do I have left? 5 minutes. Okay, so I'm double speed again, exponential speed now. So this Coulomb gas integral, they are not always closed expression for them, except in some cases. So for instance, if you look at the maximum on the whole circle, then it's called the Morris integral, and there is explicit formula in terms of gamma function. Or if you prefer, in terms of ratio of generalized Barnes function, which have these properties. So this is so there is a well-defined formula as a function for arbitrary number of replica. And okay, so now I'm going to accelerate because it's a bit technical here, but from this exact formula, you can obtain an expression for the Laplace transform of the free energy in a high temperature phase. So as you can see, there is a transition here at b equal 1. You see that the gamma factor here becomes singular. And so this is the expression that you get from here. It's just relabeling. I mean, you just change a variable. But the nice thing about this expression is showing you that if you multiply both sides by this gamma function here, it is actually self-dual. And it's a long story, but it is in this field of log correlated signals. It is known that for this self-dual type of quantity, there is freezing. So I will skip this because these are details about freezing. I'm not going to talk about it, but just to tell you that from this and the whole story of this field, then we get this exact formula for the distribution, the exponential Laplace transform of the maximum, delta NM of the signal. Okay, so from this one can get cumulants, and you can do the same for the small interval using Selberg integrals. So we can do the circle, the full circle, and a smaller interval. And the results are as follows, and they are interesting. So if you look at the cumulants, it turns out that there are actually two parts. One which come from the microscopic scales, which are related to this fermionic nature of the signal, of discreteness of the signal, if you want, at the microscopic scale. And we obtain from the formula I showed you before, we obtain this expression for these cumulants. And then there is another contribution which comes from the large scale of fractional Brownian motion, and which actually we had already derived in a previous paper with Shanyu Kao. So they have some expression again with Barnes function. I'm not going to give too much detail on that. Okay, so let me jump now to the last part of the talk. So these are some numerical checks. So let me now go to this last part, which are interacting fermions now in one dimension in some potential. And we're going to use what we have said before in the second part of the talk. Okay, so now let's go back to one dimension and to fermions, and now add some two-body interaction between the fermions. And there is a question one can ask is to what are the potential and two-body interactions so that the ground state wave function has simple form, has one or two-body form. So this question goes back to Calogero, and but we have studied a bit systematically this and classify a bit the possible potentials a bit beyond that by allowing for an external potential. So the simplest case is a Scalogero-Sutherland model, but it belongs actually to a larger family of class which can be mapped to random matrix ensembles. So there is a map, so you can identify psi0 square with P of lambda. This is a matrix potential for the random matrix ensemble, and this is Van der Monde to the power beta. So there is, so you can find some maps which allow to map position of fermions to eigenvalues in some cases. So we did a search, an exhaustive search, but these are the classical examples, which I will not detail too much, but here we have the harmonic, I mean, we found more examples than this, but I'm just going to talk about those. So this is just the harmonic oscillator with, this is a Calogero-Sutherland model. This is the one, the Sutherland model on the circle, which I mentioned before. And this is Wishart-Laguerre beta ensemble, which correspond in quantum mechanics to this x squared plus 1 over x squared, and this type of interaction. And then there is a Jacobi ensemble and so on. So I just want to point out that the eigen density of these ensembles are well known, so you can extract from them upon this mapping. The maps are here, and you can extract from them the density for the fermion problem. For instance, you find for the Calogero-Sutherland model of fermions, this is a mean density. So you see that the edge of the support now is square root of beta n. So it depends on beta explicitly. And similar results for the Wishart-Laguerre type of potential, and so on. Okay, so let me go now to full counting statistics. So let me recall this formula we had for the n=1 replica in this paper with Fyodorov based on this Forrester conjecture. So it has this form, and from this form, one can actually, again, this was for the C beta E ensemble, but in fact, we have a universality conjecture that the higher cumulants, so these are the higher cumulants, bigger than 4, come only from the microscopic scale, so that gives explicit expression prediction for the full counting statistics of this of all the models in the table. And for the second cumulant, we find with the same universality conjecture and from this result that if you know the variance for the non-interacting case, then you can get the variance for the interacting case for beta different from any beta. The only change is a change in scale, and there is a shift in this constant. So this constant C beta is actually, it's a beta generalization of the Dyson meta constant. And I don't think it was known before, but this is what we obtained. And it recovers those classical values for the beta =1, 2, and 4. And so we did some check of this formula, which I won't get too much into details, except that there is a very funny even odd effect. So this is this constant C beta coming from exact diagonalization of the C beta U ensemble and so on. And, or maybe it was, no, sorry, G beta ensemble. So it fits very well with the formula for small beta. And here, these are the data points. And if you want the fit to be almost perfect, you just have to average even and odd. So there is an even odd effect in the finite size correction, which seems almost perfect and matches the formula if you average over this even and odd. Okay, and just to finish, from this full counting statistics, if you have this time now, I'm going back to non-interacting fermions. Then there are a standard formula from the cumulants to get the Rényi entropy. So that's what we get. And now let me conclude. So we have studied height function, counting staircase for general potential. We have obtained a variance to leading and subleading order. Using a universality conjecture and the Forrester Frankel conjecture, we obtain full counting statistics and entanglement entropy for non-interacting fermions, and which can be then extended, I mean, for the full counting statistics can be extended to interacting case for some specific models of the Calogero-Sutherland, for instance. We obtain for non-interacting fermions results for spherical domain in higher than 2 dimensions. We also looked at the extrema of the height function and found that there are contributions from microscopic scale and macroscopic scales, which are not trivial. And we also have some results about the edge, but I haven't shown them. So as you can see, there are a lot of conjectures, and we did some numerical tests, but there's also very nice confirmation also for this value of beta, where Buckingham and Botner obtain exact full counting statistics at the edge. And we showed that we can exactly match the result coming from the bulk to the edge with our formula for any beta at the price of some completely amazing relation between Barnes function, which I didn't suspect could exist, but okay. I haven't shown them here, but they are pretty scary. Okay, but they work. Okay, so now there are some possible extensions, and I will stop because I went over my time.
Thank you very much. Are there any questions?
Yeah, for the first part of your talk, I guess these full counting statistics are related to vertex operator correlation functions
What, sorry?
two correlation functions of vertex operators in homogeneous CFT, right? So did you compare
probably.
with supposedly the results of Dubai et al. Will provide? Did you compare with that or?
Well, I mean, they have some results, but for instance, okay, yeah, of course we compare with their results. Explicit result, I mean, about the variance, for instance, for an interval. But we have somehow for this variance for interval, we have more precise results actually.
So they're missing something.
Well, I mean,
some
they certainly
regularization.
have the, yeah, I have to remember exactly. I mean, they certainly have the leading term correctly. There's no question.
Yeah, yeah.
But about the sub-leading term, it's not. I don't think they. Okay, I don't remember offhand now, but I think there was some difference. But yeah.
With the regular,
they had to scale things a bit differently, I think.
Right. Okay. So, and the question: did you look at finite temperatures? Are you able to access that?
We're supposed to do it now.
Because there are other results. There are other results available for finite temperatures.
At finite temperature.
Yeah. Okay, we can look at. Okay.
From what? In homogeneous bosonization.
For instance, quantum statistics in homogeneous potential at kind of large enough temperatures or long enough distances that are quite large compared to the temperature length.
Yeah.
Then there's some asymptotics one can write.
Okay. Well, okay.
So if you can access that, that'd be nice.
Yeah. It, but, okay.
Any other questions? That's up. He's next. So.
Okay. For non-interacting, you managed to introduce this Gaussian field, but I wonder, can you do also for interacting case? Because that would be very natural from the bosonization point of view, right?
Well, I mean, there is of course there's a Luttinger liquid
exactly.
representation which gives the leading term again in the variance, but doesn't give the sub-leading term. So if you want the sub-leading term, you really have to work harder. But yeah, there's probably also some Gaussian free field. Certainly for beta equal 1, 2, and 4, there is Gaussian free field representation, but
right, and then
when I mean Gaussian free field representation, I mean okay. So we need not just macroscopic scales, but we need also microscopic scales. So we need to know the Gaussian free field at all scales, and for this there are much less results. So it was very important here that it is the Gaussian free field at small scale is regularized by the sign kernel.
Okay. And very quick question. So how do you explain in your statistic you have t-square behavior, e to the t-square, but how does it fall Gaussian? Because
you mean in this at the end of the talk here?
Yeah. Just normally I would expect linear dependence, no? In full quantum statistics.
T here is just a parameter.
Sorry.
Yeah. You're talking
here.
About this formula.
Yeah.
Yeah. So t is the Laplace parameter. So t square is the Gaussian part. Okay, and this is coming from microscopic part. I mean, so that's coming from large scale, and this is coming from small scale, and it has a complicated form.
All right, maybe we discuss in private. Thanks.
Yeah, so actually it's a related question. So for the non-interacting case, you compute the variance starting from scratch, like from the single particle wave function, WKB and stuff. Yeah. So then a related question. So how difficult would it be in principle to show that the higher cumulants they are suppressed with respect to the variance, which is log?
I don't know how to do it. I mean, we had to rely on the random matrix results, and then argue that somehow it was universal. Certainly, they are the same. I mean, they are consistent for a different value of beta, and so there's a universality conjecture there. I mean, the conjecture is that higher cumulants come only from the microscales, so you can read them on some random matrix models.
Yes,
okay. But this is a conjecture. I mean, we don't. The only maybe check we have is really this Dyson meta constant, which I showed you here numerically, but
Okay, no, thanks.
Any other questions? If not, let's thank